Okay, so I just want to go through some stuff about more details about the diffraction grating that I didn't have time to go through in class the other day because it might be useful. So I'm going to go through several stages. I'm just going to start with like one color and we're going to build up to what happens with the white. So if we take a diffraction grating, like filter with lots of like individual like lines on it very close together, and you shine monochromatic red light, so like a laser at it, it's a single wavelength of light, we always get a central antinode, n equals 0, because along that central line, the path difference between adjacent sources is always 0. It was 0 wavelengths, but that's true for any wavelength. So you always get that central one. Now you're also going to get off to the sides a path difference of 1 wavelength between adjacent sources. So the light from each source has traveled 1 additional wavelength. So they still arrive at that point in phase and constructively interfere. And you're going to get n equals 2, where it would have traveled 2 extra wavelengths. So you've got a path difference of 2 wavelengths, and you're going to get constructive interference there. And that carries on. I'm only going up to n equals 2 in these diagrams just to make it simpler, but it carries on. Okay, so that would on a screen look like a series of red lines or dots um, on a screen. Okay, now what if we were to add? Oh, sorry, uh, the um, the gaps between them. Um, Important to know that there is light shining there too. Okay, those are just nodal regions. So there is light shining there, but it's all destructively interfering. So the light coming from one source is completely in opposite phase from light from one of the other sources. So they destructively interfere, and that will be true for all of the sources. So there's there is light shining in those regions, but it is destructively interfering, so it looks dark. All right. Now, if we have a different wavelength, so let's say we take that red pattern that we've already got and we shine a green laser in at the same time, okay? And what would we see and how would it be different? Now, important to know, really important to probably remember, red has the longest wavelength of visible light, violet is the shortest. So green light will be a shorter wavelength than red light. Now, because green has a shorter wavelength, it will reach a path difference of 1 wavelength at a smaller angle. Because remember, if you start at n equals 0 in the center, where the path difference is 0, as you go further out from n equals 0, the path difference is increasing, which means that you will reach a path difference of 1 wavelength for green light before you'll reach a path difference of 1 wavelength for red light, because green has a shorter wavelength. So the green will appear closer to the center than red will. Okay. Almost notice there that the central n equals 0 is an antinode for both red and green. So it would appear yellow to us, assuming that the red and the green were both the same brightness, which if you're talking about lasers, they usually aren't. Green usually appear a lot brighter because our eyes are more sensitive to green light than red light. Um, Also important to note here that all wavelengths diffract at all angles. So like the red light or green light coming through the diffraction grating, diffract through all 180 degrees in front of the diffraction grating. The important thing is where the constructive interference occurs. Okay, you shouldn't say things like red light diffracts more. That doesn't. They all diffract at all angles. It's just there is constructive and destructive interference occurring that makes it appear brighter in some places than others. Okay. Okay. Now, so that's when we've got like two different wavelengths. But what if we've got all the wavelengths? So what if we take white light, which has all the visible wavelengths in it? And what do we get when we shine that through a diffraction grating? Now, as with all the ones we've already seen, we always get an antinode for all wavelengths in that n equals 0 position, okay? The path difference is 0 wavelengths for all wavelengths. So it's a constructive interference and an antinode for all wavelengths, so it looks white. Okay? But when we start going out further, it gets a little bit difficult. Okay, now a bit wordy here, but I've got it written there. So visible light with the shortest wavelength, which is violet, has a path difference of 1 wavelength closer or at a smaller angle than the others. Okay? Because it's got the shortest wavelength, it will constructively interfere at the smallest angle, forming an antinode, and it will appear bright at a smaller angle. And as you go outwards, each subsequent wavelength or color will form a bright antinode at a slightly larger angle. So if violet appears here at the start of, so that's like the n equals 1 and the n equals 2 lines, just outside that you'll find will be all the other colors, okay? As you gradually increase the wavelength. I've just shown a few lines here, but remember they're not individual lines, it's a whole spectrum, okay? Which means that what you'll see is something like this. You'll get the n equals 0 white line, because they all constructively interfere there. And then at n equals 1, you'll get a spectrum. Now, at n equals 1, the path difference is one wavelength for all the wavelengths, but the shortest wavelength, the violet, will be closest to the n equals 0. And as you go gradually further out through blue and green and yellow and orange out to red, the wavelength is gradually increasing. But they all have a path difference of one wavelength. When you get out to 2, n equals 2, the path difference is two wavelengths for all wavelengths. Again, the shortest wavelength will be closest to n equals 0, and the second one will be dimmer than the n equals 1 spectrum. And again, I've just shown n equals 1 and out to n equals 2, but there could be more. Okay. Again, as before, the dark spaces, where there are dark spaces, I'm going to come back to that in a minute. The dark spaces between the spectra are where all visible wavelengths of light destructively interfere. Okay, so there is light shining in those dark spaces, but it's destructively interfering. So you get spectra, so you get n equals 0 white line and n equals 1 spectra, n equals 2 spectra, etc. All right, now the stuff I'm going to go through now, strictly speaking, not necessary, but it's interesting, could be useful for scholarship, and it's kind of interesting just to see what the stuff actually looks like. So if you want to go and work on some revision stuff or some other stuff now, that's fine, but I'm going to go through some stuff here anyway. So I was just referring to the gaps between the spectra and how the fact that there's not actually always a gap between spectra. In fact, usually there's not a gap between spectra. I thought I'd just go through that quickly, why that is. And the fact they actually usually end up overlapping. If we take the standard interference pattern formula, d sine theta equals n lambda, now the maximum angle we can have diffracting, remember that 0 is that n equals 0 straight ahead, so the maximum you can go either side is 90 degrees from that, which means that the maximum n you can get is when it's 90 degrees, which if we rearrange that, the maximum n will be d, the gaps, the spacing between the sources divided by the wavelength. Like we've already sort of talked about that. So it's basically how many wavelengths fit between the sources. That's your maximum n. Okay. Now, if we take a fairly typical diffraction grating is 600 lines per millimeter or 600,000 lines per meter. That would give us d is 1 divided by 600,000, so 1.67 times 10 to the minus 6 meters. Now, if we look at what the maximum n we get for different parts of the spectrum, so if we take violet, which is the shortest wavelength end, and we put the d divided by lambda, so 1.67 times 10 to the minus 6 divided by the wavelength, which is 400 nanometers, or approximately 400 nanometers, we get an n of 4.2. That means, now there can't be 0.2, but there will be 4 violet antinodes either side of the central n equals 0. So that means there would be, including those, and on both sides, there would be 9. So 1 in the middle and 4 on each side. So there would be 9 violet antinodes. But if we look at red, if we do the same thing with red, so 1.67 times 10 to the negative 6 divided by 700 nanometers, we only get 2.4, which means that there will be 2 each side and the 1 in the middle, so 5 in total. So that means on each side of the central white, we've got 4 spectra starting at violet, but only 2 of them are completed. There's only 2 of them that actually complete through to red. So that at least 2 of them must overlap in this, okay? So we can actually have a look, where does that actually start? What does the spectra actually look like? If we could see all of it, because remember, most of it's going to be too dim for us to see, but if we could see it, what would it look like? So again, if we take that d sine theta equals n lambda, now, if we look at the nth spectrum for red, okay? So that's the end of the spectrum for red. So the end of the nth spectrum, and we want to see where does the next one start. So that'll be the n plus 1th spectrum, and it starts with violet. So we've got one spectrum ending with red and the next one starting with violet. And if we want to know where that actually overlaps, all we have to do is make those two terms equal because they've both got the same d, the same source spacing, and it's the same theta. They occur at the same place. So we can just make n red, n times the wavelength of red equal to n plus 1 times the wavelength of violet. Now you notice that this actually doesn't matter what the slit spacing is, so actually the source spacing and the angle, but it will tell us how many there are. Okay, I'm not going to go through how to rearrange that, but then you math it and basically you get this. Okay, n is the wavelength of violet divided by the difference between the red and the violet wavelengths, which is 1.33. That means that once you get beyond n equals 1.33, the spectra overlap. That means that the only spectrum that doesn't overlap with another one is the n equals 1, or the n equals 0. Okay, so the n equals, if you go to n equals 2 or further, the spectra all overlap. And that is independent of what the spacing of the diffraction grating is. Like it will, if you have a different spacing, it will occur at a different angle, but the n equals 2 and beyond spectra will still always overlap. Yeah, so beyond n equals 1, all spectra overlap for all diffraction gratings. Now, try to animate what this looks like. So, um, if we just imagine this is like 90 degrees wrapping around either side, I've just had to draw it sort of in a fixed space. But if you imagine this kind of wrapping around you, so it goes around to like 180 degrees, sorry, 90 degrees either side. So we have an n equals 0 white line in the middle. Okay, that's the same as we always have. And now I've tried that these are actually pretty close to the correct angle, so I went and calculated them all. The n equals 1 spectra either side are somewhere between like about 25 and no, sorry, 13 and 25 degrees or something like that. Can't remember the numbers exactly off the top of my head. The n equals 2 are a little bit further out, about 28 degrees to about 50 something degrees. And you notice that it's spread out a lot more, and it's also dimmer. I've tried to make it a little bit dimmer. In reality, it would be a lot dimmer than that, but just to make it. Now, those are the only, remember, n equals 1 is the only one that doesn't overlap. So n equals 2, when we get to n equals 3, now I've just drawn it above, so it's a bit clearer. It is actually spread out quite a lot. And you notice that this one doesn't finish. The violet starts at about the green of the n equals 2, but it doesn't finish. It only gets up to about yellow in the spectrum before it hits 90 degrees. And the n equals 4 barely gets out of the violet. Okay, so it starts at about 75 degrees or something like that, and it goes all the way around, and it barely gets out of the violet before it hits 90 degrees. So we get all these, and they're gradually getting dimmer as you go further out. And if you actually overlap them all like you would see it, it looks something like this. So you get this like you get this quite clear n equals 1 spectrum, but once you go outside that, if you could see it, it's quite muddled and in terms of what the colors actually look like. So that's some more details on those diffraction grating patterns. Hope that's cleared some things up and not made things worse. If you have any questions, feel free to email me.